There is a telescope 1,000,000 miles from Earth, and in more than 32,000 hours of looking back toward the dawn of the universe, it has photographed something nobody can explain. They appear in nearly every image of that ancient era, small, red, dense points of light scattered across the first billion years of cosmic history. Astronomers call them the little red dots, and the more carefully we study them, the stranger they become. They are too bright for their size, too massive for their age, and they fit no model of how a star, a galaxy, or a black hole is supposed to form. They flood the early cosmos, and then, 1 billion years later, they vanish completely. So here is the question we will follow tonight. What if the first chapter of the universe was building something we never had a name for? An object that is somehow both a star and a black hole at once. Get comfortable and dim the lights. Subscribe if you have not already and stay with us, because the answer the data is slowly pointing toward was quietly predicted on paper, 16 years before anyone could see one. Let's get into it. Part 1. The dots that are everywhere. There is a telescope 1,000,000 miles from where you are sitting right now, and it is looking backward in time. That is not a metaphor. The James Webb Space Telescope, parked at a quiet gravitational balance point far beyond the Moon, collects light that has been travelling for almost the entire age of the universe. When that light finally lands on its golden mirror, the telescope is not seeing the cosmos as it is tonight. It is seeing the cosmos as it was billions of years ago in a chapter of cosmic history that ended long before the Earth, the Sun, or a single atom of your body existed. And recently, in image after image of that ancient chapter, the telescope has been finding something that nobody can explain. They look at first like nothing at all. Small, red, faint, scattered like grains of sand across the oldest reaches of the universe we have ever managed to observe. Astronomers have given them a name that sounds almost too plain for what they may turn out to be. They call them the little red dots. And the strange thing, the thing that pulled an entire field of science to a stop, is not that we found one of them. It is that we keep finding them. Everywhere we point the telescope at the early universe, there they are again. The same compact red glow showing up in survey after survey, as if the dawn of the cosmos had been quietly seeded with them. And here is the part that should make you sit up, even if you are listening with your eyes closed and the lights already low. We do not know what they are, not vaguely, not approximately. We genuinely do not know. The more carefully we study the little red dots, the stranger they become, and the further they drift from anything our models were built to describe. They do not fit our picture of how a star forms. They do not fit our picture of how a galaxy assembles. They do not fit our picture of how a black hole is born. They sit outside all three, in a category that, until a few years ago, did not exist. So tonight, settle in, because this is a story about a mystery that is still open, one of the genuinely unsolved problems in modern astrophysics. And it is a mystery that may turn out to hold the missing first page of the universe's own origin story. To understand why these little red dots matter so much, you first have to understand just how unlikely they are. And to understand that, we have to talk about the machine that found them. The James Webb Space Telescope launched on December 25, 2021. A Christmas morning launch, after decades of delays, billions of dollars, and a long-held breath from everyone who had staked a career on it. It unfolded itself in the dark, a mirror made of 18 gold-coated segments, a sunshield the size of a tennis court, and then it began to work. And it has not stopped. In the years since, Webb has logged more than 32,000 hours of observation. It has sent home more than 600 terabytes of data. To put that number somewhere, you can feel it. 600 terabytes is enough to fill the storage of more than 2,000 modern smartphones. Every photo, every video, every file 2,000 phones could hold, and all of it nothing but the early universe. Somewhere inside that ocean of data, a pattern surfaced. It did not announce itself. Nobody pointed the telescope at the little red dots on purpose because nobody knew they were there to be found. They turned up the way the most interesting things in science often turn up, as an uninvited guest. Astronomers were running surveys with other goals entirely. Two of them, programs named Eager and Fresco, were designed to hunt for galaxies at extreme distance, to examine the era roughly 500 million to 1 billion years after the Big Bang. That is deep time. That is the universe as a toddler, still figuring out how to build the structures it would spend the next 13 billion years refining. And as Webb scanned that era, nearly every image it returned carried the same strange object. A little red dot, and then another, and another. By 600 million years after the Big Bang, it begins to look as though the early universe was simply full of them. Imagine that for a moment. An entire epoch of cosmic history, populated by a kind of object we have no name for and no theory to explain. They were hiding in plain sight. They had been sitting in the deep field images all along, in the sense that the light was always arriving, but no telescope before Webb could actually see them. The Hubble Space Telescope, for all its glory, was calibrated for shorter wavelengths than these objects emit. Earlier infrared telescopes lacked the raw sensitivity to look this far back. The little red dots needed an instrument tuned to exactly their kind of light, and Webb was the first one ever built. So they waited. They waited through every previous generation of astronomy, invisible, until the right machine arrived to notice them. That phrase is going to matter later, so hold on to it. Hiding in plain sight. We will come back to it. Because by the end of tonight, that simple idea that something can be everywhere and still be unseen until the right eyes arrive is going to mean something much larger than a population of distant red specks. For now, just sit with the strangeness of the situation. A telescope built and launched within your own lifetime turned its mirror toward the first chapter of the universe and found that chapter crowded with objects that should not be there. The obvious question is the one a child would ask, what are they? And the honest answer, the one that makes this a story worth 2 hours of your night, is that the people who found them still cannot tell you. Before we go any further, it is worth slowing down on that idea of looking backward in time, because the whole night depends on it, and it is easy to let it slide past as a figure of speech. It is not a figure of speech. Light is fast, but it is not infinitely fast. It travels at a fixed and finite speed, and that means light always carries a delay. When you look at the moon, you see it as it was a little over a second ago. When you look at the sun, you see it as it was 8 minutes ago. If the sun were to vanish, you would have 8 minutes of ordinary sunshine before the sky noticed. Look at the next star over and you are seeing years into the past. And when you look at the little red dots, you're seeing light that left them more than 13 billion years ago, before the Earth had formed, before the sun had ignited, before the atoms that make up your body had been forged in the cores of stars that themselves no longer exist. The little red dots you have been hearing about may not exist anymore at all. Whatever they became it billions of years ago. We are not watching the early universe in a recording. We are watching the only copy there is, arriving live, one ancient photon at a time. That is what makes a telescope like Webb less an eye and more a kind of time machine. A machine whose entire function is to catch the oldest light still in transit and read it before it passes us forever. And it means the little red dots are not simply far away. They are long ago. They are a feature of the universe's childhood, and the fact that we can study them at all is a quiet accident of physics. That the universe is the right age, and we are the right distance for that ancient light to be reaching us in exactly this era. A civilization that arose much earlier would have been too soon to see them clearly. A civilization much later might find the light too stretched and faint to read. We happen to have arrived at a moment when the dawn of the cosmos is still legible. That is worth holding on to as the night goes on. Part 2. A population that switches on and off. When astronomers first began to take the little red dots seriously, they did what scientists always do with something new. They tried to measure it. If you cannot yet explain a thing, you can at least describe it. Write down its size, its brightness, its colour, its age, and trust that the description will eventually corner the explanation. So that is where we begin. Not with what the little red dots are, but with what we can actually say about them. And even the description, it turns out, is unsettling. Start with size. The little red dots are extraordinarily compact. A typical one is no more than about 500 light-years across. Now, 500 light-years sounds enormous, and in human terms it is a distance light itself needs 5 centuries to cross. But on the scale of galaxies, it is tiny. Our own Milky Way is roughly 100,000 light-years wide. That makes a little red dot something like 200 times smaller than the galaxy you live in. Picture the Milky Way shrunk down until the entire thing, All 400 billion stars would fit 200 times over inside the space it now occupies. That is the kind of object we're talking about. Small, concentrated, dense in a way that, as you will see, becomes a serious problem. Now add brightness. You might expect something this small, this far away, and this ancient to be faint to the point of near invisibility. Instead, the little red dots burn unusually bright for their size. They are luminous out of all proportion to how compact they are, and they are very, very red, which, as plain as it sounds, is the single most important clue in this entire story, and the reason they evaded us for so long. Their characteristic light falls in the mid-infrared, a band of the spectrum that human eyes cannot see and that, until Webb, our telescopes could barely reach. And then there is the property that genuinely stops you. With every telescope we have ever built, including the most powerful one in human history, we cannot see any structure inside a little red dot. None. When we look at a normal galaxy, even a distant one, we can usually make out something of its shape. A hint of spiral arms, a bright central bulge, a disk, an outline. Galaxies look like the sprawling structured things they are. But the little red dots show us nothing of the kind. They appear as single points of light, dots. They look the way a star looks to your naked eye on a clear night, an unresolved pinprick with no detail to be teased out no matter how hard you stare. Webb has the sharpest vision of any telescope ever made, and it looks at a little red dot and sees a point. That fact alone forces a hard fork in the road, and it is worth pausing on, because the script of the next 2 hours runs straight through it. If the little red dots show no internal structure, there are only two possibilities. Either they are genuinely, almost impossibly tiny, too small for any structure to exist, or their light is so completely dominated by a single, blindingly bright source at their centre that it simply drowns out everything around it, the way a single streetlight at night can wash an entire dark street out of your vision. One central thing, so bright that the rest of the object disappears into its glare. Keep both of those possibilities in your mind. By the end of the night, one of them is going to win, and the winner is stranger than either sounds right now. There is one more measurement, and it may be the most haunting of all. It is not a measurement of any single dot. It is a measurement of when the dots exist at all. The little red dots are not spread evenly across cosmic history. They appear, they flood an era, and then they vanish. By around 600 million years after the Big Bang, the early universe is rich with them. They are a defining feature of that epoch. And then, roughly 1.5 billion years after the Big Bang, they are simply gone. Not rare, not faint, gone. The population switches off. Think about what that means. We are used to the idea that things in the universe change slowly. Stars live for millions or billions of years. Galaxies take eons to assemble. The cosmos on the whole is patient. But the little red dots behave like something that was switched on and then switched off. A feature of one specific chapter of the universe's life, present in that chapter and absent before and after. That is not how we expect a class of cosmic object to behave. A type of star does not simply stop existing. A type of galaxy does not vanish from the record. And so this single fact, that the little red dots have a beginning and an end in cosmic time, was one of the first things that moved them out of the category of mild curiosity and into the category of genuine mystery. It is worth dwelling on the compactness a little longer because it is the property that does the most quiet damage to our intuitions, and it rewards a slow look. We tend to think of brightness and size as loosely linked. Big things are bright, small things are dim, and that rough rule serves us well enough in everyday life. A bonfire outshines a candle. A city outshines a street lamp. But the little red dots break that rule in the most flagrant way. They are tiny, and they are luminous, and those two facts together describe an object of staggering concentration. Imagine taking the light of something enormous and forcing all of it to come out of a space far too small to hold it. Imagine the output of a great city squeezed down until it all radiates from a single window. The little red dots are, in that sense, the cosmic equivalent of light, pressed under impossible pressure, and pressure is exactly the right word because an object that bright and that small is an object where the physics is being pushed hard against its limits. And density has consequences. A thing that concentrated is a thing where gravity is fierce, where matter is crowded, where the gentle, slow processes that build ordinary galaxies simply cannot operate the way they usually do. When you find an object that is both very small and very bright, you have not found a scaled-down version of something familiar. You have found a place where the rules are being tested. That is the real reason the compactness unsettled astronomers. It was not just an awkward measurement. It was a signal that whatever the little red dots are, they were assembled by a process that favours extreme concentration. And extreme concentration, as you will see by the end of the night, points toward one particular kind of object more than any other. Because a thing that turns on and off is a thing with a cause. Something made the conditions right for the little red dots, and then, later, something made those conditions go away. If we could understand the switch, we would understand the dots. So we have our description now. Tiny, 200 times smaller than the Milky Way. Bright, out of all proportion to that size. Deeply, strangely red. Structureless, a pure point of light even to the sharpest telescope ever built, and bounded in time, flourishing in one early window and then disappearing completely. Every one of those properties is a thread, and when astronomers began, carefully, to pull on the first of them, the redness, the whole thing started to come apart in their hands. Because the redness, when they finally looked at it closely, turned out to run far deeper than anyone expected. Part 3. The redness that runs too deep. Of all the properties of the little red dots, the colour seems at first like the easy one, the one you could explain on a quiet afternoon without much trouble, because in astronomy, redness usually has a simple and well-understood meaning, and to see why, you only have to think about a sunset. When the sun sits high in the sky at noon, it looks white, or pale yellow, but when it sinks toward the horizon in the evening it turns orange, then a deep, heavy red. Nothing about the sun itself has changed in those few hours. What has changed is the path its light takes to reach your eye. At sunset, the sun's light has to travel through far more of Earth's atmosphere, a long, low, slanting path through thick air, and air, along with the fine dust and particles suspended in it, is much better at scattering short blue wavelengths of light than long red ones. The blue gets knocked out of the beam, bounced away in every direction. The red survives the journey. So the sun, stripped of its blue by the long trip through the atmosphere, arrives at your eye looking red. That is the sunset, and it is a genuine piece of physics you can carry with you straight into deep space. There is also a second, grander reason that distant things in the universe look red, and it is the one astronomers reach for first. It is called redshift. The universe is expanding. The fabric of space itself is stretching, carrying galaxies apart from one another. And light travelling through that stretching space gets stretched along with it. A wave of light that began its journey with a certain wavelength has that wavelength physically elongated, drawn out, as space expands beneath it, and longer wavelengths are redder. So the longer light has travelled, the more space has stretched during its trip, and the redder it arrives. Redshift is one of the most reliable tools in all of astronomy. It is, in fact, how we measure cosmic distance and cosmic age in the first place. The redder an ancient object looks, the further back in time we're seeing it. So when astronomers first saw how red the little red dots were, the obvious first thought was simply, of course they are red. They are among the most ancient objects we have ever observed. Their light has been travelling for almost the entire history of the universe. Of course it has been stretched. Of course it arrives red. The redness at first glance was not a mystery at all. It was a confirmation, a sign that we really were looking at the deep past. But science does not stop at the first glance, and this is the moment the story turns. Because astronomers did not simply note that the little red dots were red and move on. They took that red light and they broke it apart. They spread it out into a spectrum, separated it wavelength by wavelength, the way a prism fans sunlight into a rainbow, so they could examine the structure hidden inside the colour. And when they did that, they found something that the expansion of the universe could not account for. The little red dots were redder than redshift alone could explain. Stretch the light all you like for its billions of years of travel, run the numbers as carefully as you want, and you still come up short. There was an excess of redness. Something beyond the expansion of space was reddening these objects. And that excess was the first genuine crack in the easy explanation. The first sign that the little red dots were not going to be simple. Think about how strange it is for a moment that we can even make this kind of statement, that we can say an object is redder than its distance allows. We're talking about specks of light from the dawn of the universe, unimaginably far away, and yet astronomers can speak about their colour with the confidence of someone describing a paint sample held up to a window. That confidence comes from a long chain of careful work. The expansion of the universe is not a vague idea. It is measured, calibrated, pinned down by decades of observation, so that for any given object, astronomers can calculate quite precisely how much redshift its distance should produce. That calculated redshift is a baseline, a prediction. And when the little red dots came in redder than the baseline, the gap between prediction and measurement was not noise. It was a real, quantified excess, the kind of discrepancy that a scientist cannot explain away and would not want to. There is a lesson in that gap, and it is the lesson the whole night turns on. Mysteries in science very rarely arrive as something loud and obvious. They almost never announce themselves. They arrive as a small disagreement between what you predicted and what you measured, a number that comes in slightly wrong, a curve that bends a little where it should have run straight. The amateur instinct is to assume the measurement was sloppy and move on. The scientific instinct is to trust the gap, to take it seriously, to ask what the universe is telling you through that small stubborn disagreement. The excess redness of the little red dots was exactly such a gap. It would have been the easiest thing in the world to wave it away. Instead, astronomers leaned into it, and leaning into it is what led, eventually, to everything else tonight. So if redshift could not finish the job, what could? The researchers' first instinct took them right back to the sunset. Dust. Remember, at sunset it is the air and the fine particles within it that strip the blue out of the sun's light. Dust does the same thing on a cosmic scale. Cosmic dust, vast clouds of fine particles drifting through and around galaxies, scatters short, blue wavelengths far more effectively than long red ones. So if there were a thick veil of dust sitting between us and a little red dot, that dust would filter the object's light, scattering away the blue, letting the red pass through, and the object would arrive at our telescopes looking redder than it truly is. It is the exact same physics as the evening sky, just played out across billions of light years instead of a few miles of atmosphere. Dust was a reasonable, even elegant, first answer. The redness runs deeper than redshift. Fine. There is dust in the way, mystery contained, and it is genuinely the right first move that should be said clearly because it is easy, knowing how the story ends, to treat the dust idea as a misstep. It was not a misstep, it was good science. When you meet a new puzzle, you do not reach first for the exotic explanation. You reach for the known one, the ordinary one, the one that has solved 100 problems like it before. Dust is real, dust is everywhere in the universe, and dust reddens light by exactly the mechanism a sunset shows you every clear evening. To propose dust was not a failure of imagination. It was the disciplined thing to do, to ask of any new mystery first, whether something familiar could account for it, and only to escalate toward the strange when the familiar has been fairly tried and found wanting. The whole shape of tonight's story is that escalation, done honestly. Dust first, then starburst galaxies, then ordinary black holes, each one a reasonable, well-grounded attempt to keep the little red dots inside the universe we already understood. And only when every familiar door had been tried and everyone had failed did astronomers finally allow themselves to reach for something genuinely new. That is not the universe being perverse. That is science, earning its way, step by careful step, toward an answer strange enough to be true. Except a careful scientist does not accept a reasonable answer simply because it is reasonable. A careful scientist tests it. And the little red dots were about to be handed to one of the most precise instruments ever flown into space, an instrument whose entire job is to read the fingerprints hidden inside light. The dust idea was about to be checked, and like the easy explanations before it, it was not going to survive the checking, because when astronomers turned that instrument on the little red dots, the spectrum that came back was not the spectrum of dust. It was not the spectrum of anything they had seen in the distant universe before. It was a shape that, the moment it appeared on their screens, told them this was going to be much harder and much stranger than a veil of cosmic dust. To understand what they saw, we need to look at the light itself, and at the single sharp feature buried inside it that would, eventually, crack the whole mystery open. Part 4. The Fingerprint in the Light. The instrument astronomers turned to is called NIRSpec, the near-infrared spectrograph aboard the James Webb Space Telescope. And to understand why what it found mattered so much, you need to understand the quiet magic of what a spectrograph actually does. Because a spectrograph does something that, when you really think about it, sounds almost impossible. It lets you stand on Earth and determine what a distant object is made of simply by examining its light. Here is how that works. When you take the light from a star or a galaxy or a little red dot and you spread it out into a spectrum, a long band running from blue through to red, you're not just looking at colour, you're looking at a record. Because every element in the universe interacts with light in its own specific, unchangeable way. Each element absorbs light at its own particular set of wavelengths, and emits light at its own particular set of wavelengths. Hydrogen has its pattern, oxygen has a different one. Iron, carbon, helium, each has a signature as unique as a fingerprint. So when light passes through a cloud of gas on its way to your telescope, that gas leaves marks on the light. It removes specific wavelengths, punching dark gaps into the spectrum at exactly the places its elements absorb. Read the gaps, and you can read the gas. You can tell from billions of light years away what the light travelled through to reach you. That is what a spectrograph is for. It turns light into a chemical report. There is something almost unreasonable about that, and it is worth letting it land before we go on. For most of human history, the composition of the stars was considered the very definition of an unanswerable question, the textbook example of something we could never possibly know. A famous philosopher once used the chemical makeup of the stars as his go-to illustration of permanent human ignorance, the thing we were simply not built to find out. And then, within a few decades, spectroscopy quietly proved him wrong. Not by going to the stars, but by reading their light. Every element, heated, glows in its own private set of colours, and absorbs its own private set of colours, and that pattern never changes and never lies. Hydrogen in a distant galaxy leaves exactly the same fingerprint as hydrogen in a laboratory on Earth. So the light itself became the messenger. We did not have to travel to the dawn of the universe to learn what it was made of. We only had to catch its light and know how to read it. The little red dots, in that sense, mailed us a letter 13 billion years ago, and NIRSpec is the instrument that opens the envelope. So astronomers fed the light of the little red dots into NIRSpec, fully expecting to read the report and settle the dust question one way or the other. And the report that came back was not one they had a category for. The little red dots were emitting a great deal of blue and ultraviolet light from the short, high-energy end of the spectrum, and they were emitting a great deal of red and infrared light from the long, low-energy end. But in the middle, in the band between those two extremes, there was very little. The spectrum dipped down in the centre and rose up at both ends. If you sketched its shape, you would draw something like the letter V, a strong left side, a strong right side, and a sagging valley in between. This is what astronomers came to call the V-shaped spectral energy distribution, and when they first saw it, it stopped them, because nothing they knew of in the distant universe produced a shape like that. A dusty galaxy does not look like a V. A normal early galaxy does not look like a V. The V-shape was not on the menu. It was the spectral signature of something genuinely outside the existing catalogue, and that, all by itself, told astronomers that the dust explanation was in serious trouble. But the V-shape was not the only thing in the data. Buried inside the spectrum was one sharp, specific feature, and that feature was a clue with a name. At a wavelength of 364.6 nanometers, the spectrum of a little red dot does something abrupt. It jumps. Light with wavelengths just a little shorter than that value is being heavily absorbed, swallowed, removed. Light with wavelengths just a little longer passes straight through, unobstructed. So the spectrum has a step in it, a sudden cliff edge, where one side is dark and the other is bright. And this feature is not new to astronomy. It is old, familiar, and well understood. It has a name. It is called the Balmer break. And when you see a Balmer break in the light of a distant object, it is telling you something very specific about what that light has passed through. To understand the Balmer break, picture the inside of an atom, and picture the electrons around it not as planets on smooth orbits, but as something more like rungs on a ladder. An electron can sit on this rung, or that rung, or the one above it, but it cannot hover in the empty space between rungs. The rungs are fixed. They are the only places an electron is allowed to be. Now, when a particle of light, a photon, comes along and strikes that atom, something can happen, but only under one strict condition. The photon can lift an electron from a lower rung to a higher rung. But to do that, the photon must be carrying exactly the right amount of energy, precisely the energy of the gap between those two rungs, not a little less. If the photon carries the right energy, it gets absorbed and the electron climbs. If it does not, the photon passes by, untouched, and the atom ignores it. And this is where the specific number comes from. For hydrogen, the simplest, most abundant element in the universe, the wavelength 364.6 nanometers corresponds to a very particular event. It is the exact energy needed to take an electron sitting on hydrogen's second rung and lift it free of the atom altogether, to break it loose entirely. Any photon with a wavelength at or below that value carries enough energy to do the job, and so it gets absorbed by the hydrogen. Any photon with a wavelength longer than that does not have enough energy, and so it sails straight through. That is the cliff edge. That is the Balmer break, a sharp step in the spectrum sitting at exactly the wavelength where hydrogen stops being transparent and starts being a wall. It helps to picture the wall from the photon's point of view. Imagine a stream of light of every wavelength heading toward a cloud of hydrogen. The long wavelength, low-energy photons arrive, knock politely against the hydrogen atoms, and pass straight through. They simply do not carry enough energy to do anything, and so the hydrogen lets them by as if it were not there at all. But the short wavelength, high-energy photons arrive carrying exactly enough energy, or more, to tear an electron free of the atom. And those photons do not pass through. They get absorbed, swallowed, spent on the work of ionizing the gas. So if you stood on the far side of that hydrogen cloud and looked back at the light coming through, you would see something abrupt, a clean dividing line. On the long side, the light comes through bright and unbothered. On the short side, it has been gutted. That dividing line at 364.6 nanometers for hydrogen is the Balmer break. It is not a gradual fade, it is a border. And borders in a spectrum are gifts to an astronomer, because a sharp feature is a feature you can measure precisely, argue about precisely, and ultimately use to corner the truth precisely. The little red dots had handed astronomers a border. The only question left was what stood on the other side of it, so the presence of a Balmer break carries a clear message. It tells you there is hydrogen, a lot of hydrogen, sitting between the light source and your telescope. And there is one more detail in it, a subtle one, that becomes important later tonight, so tuck it away. The sharpness of the break matters. A messy, complicated object, an ordinary galaxy, full of stars at 1,000 different temperatures, their light filtering through gas at 1,000 different densities, produces a Balmer break that is smeared and gradual, a soft slope rather than a hard step. But a sharp, near-vertical break, a clean cliff edge, tells you something more particular. It tells you the hydrogen you are looking through is unusually pure, unusually uniform, a smooth, even atmosphere of it rather than a chaotic jumble. For now, though, the astronomers studying the little red dots had what looked like a real solid clue. A Balmer break in the light of a galaxy has, historically, one standard explanation. Hydrogen, in quantity, illuminated by young, hot stars, lots of them. The Balmer break is the classic signature of vigorous recent star formation. And so, looking at that sharp step in the spectrum, the astronomers felt the floor steady under them at last. The little red dots, they reasoned, must be early galaxies in the middle of a furious burst of starbirth. It was a real explanation, grounded in real, well-tested physics. The universe had handed them a fingerprint, and the fingerprint seemed finally readable. They had a theory. The trouble was that the theory was about to be tested against arithmetic. And arithmetic, unlike a hopeful idea, does not bend. Part 5. The elegant answer that failed. Let us give the first theory its proper name and its fair hearing, because it deserves both. The idea was that the little red dots are starburst galaxies. A starburst galaxy is exactly what it sounds like. A galaxy caught in an intense, concentrated episode of star formation, churning out new stars at a furious rate, far faster than a calm, settled galaxy like our own. And in the early universe, a time when galaxies were young and gas was abundant and everything was still being assembled, a population of starburst galaxies is not a strange thing to expect. It is, if anything, exactly the sort of thing you would expect. So the theory had the great advantage of fitting comfortably into the story astronomers already believed about cosmic dawn. And it explained things. That was its real strength. It was not just plausible, it was productive. Take the Balmer break, that sharp step in the spectrum. Young, hot stars are rich in hydrogen, and they pour out exactly the kind of light that produces a strong Balmer break. A galaxy bursting with newborn stars would naturally show that feature, so the Balmer break was explained. Take the brightness. The puzzling fact that the little red dots burn so luminously for their size. Well, pack enough young, blazing stars into a galaxy, and you get tremendous brightness. So the brightness was explained. And take the redness, the property that started this whole investigation. Starburst galaxies are famously dusty places. Furious star formation produces dust, and dust, as we have seen, reddens light. So the redness was explained too. 3 of the central mysteries of the little red dots, all accounted for by a single familiar idea. It was, in the best sense of the word, elegant. One theory, and the puzzle seemed to fold up neatly inside it. It was almost all said and done. Almost. Because there was one detail left to check, the kind of detail that an honest scientist cannot walk past, and it was this. The starburst theory leaned heavily on dust to explain the redness. So the obvious question was, how much dust would you actually need? Not in a hand-waving way, exactly how much? And could a galaxy realistically contain that much? This is the moment the theory met arithmetic. Here is the thing about dust in galaxies. It is not arbitrary. Dust does not simply appear in whatever quantity a theory finds convenient. Dust comes from stars. It is forged and shed by stars over their lifetimes. And there is a well-established, well-measured relationship between how many stars a galaxy contains and how much dust those stars can produce. Astronomers know that relationship well. It is one of the reliable rules of the trade, so you cannot just declare that a little red dot has enough dust to explain its redness. You have to count the stars first, and then the stars tell you how much dust is allowed. In late 2024, an astronomer named Caitlin Casey, working with her team at the University of Texas at Austin, did exactly that calculation. They took the little red dots. They estimated the stellar population from the optical light the objects gave off, essentially counting the stars the dots could plausibly contain. And then they applied the standard, trusted star-to-dust relationship to find out how much dust those stars could have made. They worked it through, and then they compared that number against the amount of dust you would actually need to redden a little red dot, as much as the little red dots are reddened, and their stomachs dropped. The dust they could account for came to roughly 1% of the dust the theory required. 1%. Not 80%, not half. Not a number you could rescue with a generous assumption or a tweak to the model. 1%. The starburst galaxies, even granting them every star you could reasonably pack in, could only produce 1/100th of the dust needed to explain their own colour. That is a shortfall of 2 orders of magnitude, a factor of 100, and a gap that large is not a rounding error. It is a verdict. A shortfall like that can mean only one of 2 things. Either the well-established, carefully measured relationship between stars and dust is simply wrong, and that relationship underpins a great deal of astronomy, so throwing it out is no small matter. Or the main thing lighting up a little red dot is not stars at all. And the dust was not even the theory's only problem. There was a second one, just as severe, and it had to do with the brightness. To explain the sheer luminosity of a little red dot using starlight alone, you would need to cram an enormous number of stars into that tiny, 500 light-year space. And when astronomers worked out just how densely those stars would have to be packed, the answer was, frankly, absurd. The stars would be separated by only a few astronomical units, an astronomical unit being the distance from the Earth to the Sun. Stars sitting that close together on cosmic terms is not a galaxy. It is a catastrophe in slow motion. At those densities, stars would be colliding and merging constantly. The gravitational dynamics would be wildly, hopelessly unstable. Such a configuration could not hold together long enough to be the calm, persistent objects we observe. The brightness, like the redness, simply could not be paid for with stars. So the elegant theory failed, and it failed on its own arithmetic. Not because anyone disliked it, not because of some rival's clever objection. It failed because when you took it seriously enough to do the sums refused to agree. This is in its own quiet way one of the most important moments of the night, and not just for the little red dots. It is a small demonstration of how science actually protects itself from its own wishful thinking. This starburst theory was attractive. It was elegant. It was familiar. It explained three things at once, and a great many capable astronomers found it persuasive. In almost any other kind of human reasoning, that would have been enough. A good story, widely believed, becomes the accepted truth. But science added one more step. It asked the theory to survive contact with arithmetic. It demanded that the dust be counted, not assumed. And the moment the counting was done, the beautiful story simply could not stand, and no amount of fondness for it could prop it up. The numbers did not care how elegant the idea was. There is a kind of integrity in that, and it is worth admiring even as the theory dies. The universe is under no obligation to make its puzzles solvable by our most comfortable ideas. And a field that is willing to kill its own elegant theory, on the evidence, in public, is a field you can trust, because it has just shown you that it would rather be correct than be comfortable. So when, later tonight, that same field tells you about an object as strange as a black hole star, you can take the claim seriously precisely because you have watched these same people refuse to believe something far more reasonable when the arithmetic told them not to. The death of the starburst theory is not a detour, it is the credential for everything that comes after it, and this is the first real crack in the night story, so let it land. The obvious answer, the comfortable answer, the one that folded the whole puzzle up so neatly turned out to be wrong, and when the obvious answer is wrong, you're not back where you started. You're somewhere worse, and also somewhere more interesting. Because now you know the little red dots are not a familiar thing wearing an unfamiliar coat. They are genuinely strange. The arithmetic just told you so. The blue and red light, the V-shaped spectrum, the impossible compactness, these are not the signatures of a starburst galaxy. They are the signatures of something else. And so astronomers did what scientists do when a good theory dies. They turned to the next suspect, and the next suspect was not a galaxy full of stars at all. It was one single object, sitting alone at the centre, and it was one of the most extreme objects the universe is capable of producing. Part 6. The second suspect. If the little red dots are not galaxies packed with hot young stars, then what could they be? Cast your mind back to that fork in the road from earlier, the one forced on us by the fact that the dots show no internal structure, that they appear as pure points of light. We said there were only two ways to read that. Either the dots are genuinely tiny, or their light is dominated by one single, overwhelmingly bright source at the centre, a source so brilliant it washes everything else out of view. The starburst idea was, in a sense, a bet on the first reading. A tiny crowded galaxy. It lost. So now astronomers turn to the second reading. One central object, one engine. And in the universe, when you're looking for a single object compact enough and bright enough to outshine an entire galaxy, there is one obvious candidate, a supermassive black hole. Now the phrase black hole tends to conjure darkness, an object that swallows light, that gives nothing back, the blackest thing imaginable, and a black hole itself is exactly that. But a feeding black hole, an active one, is something else entirely, and it is worth taking a moment to see why, because it is the opposite of what your intuition expects. At the centre of most galaxies sits a supermassive black hole, and around many of them swirls a vast disk of gas and dust spiralling slowly inward, a structure called an accretion disk. And as that gas spirals in, it does not fall quietly, it is compressed. It is wrenched and sheared by titanic gravitational forces. It is heated to extraordinary temperatures, well over 12 million degrees Celsius. And matter that hot does not stay dark. It blazes, it pours out light. This is the great cosmic irony. The regions immediately around the most light-swallowing objects in existence are among the brightest places in the entire universe. An actively feeding supermassive black hole can outshine every star in its host galaxy combined. It is, in luminous terms, a monster. And a monster is exactly what the little red dots seem to need. Let yourself sit with that inversion for a moment, because it is one of the genuinely beautiful facts in astronomy, and it is easy to rush past. The phrase black hole has, by now, soaked up every dark association a phrase can hold. Emptiness, swallowing, an end from which nothing returns. And the black hole itself, the region within the point of no return, earns every bit of that. But the neighbourhood just outside it does the opposite. The gas spiralling in toward a feeding black hole is the brightest furnace the universe knows how to build. It is not the black hole that shines. It is the matter in its final doomed approach, wrung out and heated white-hot by the steepest gravitational slope in nature, blazing in its last moments before the fall. So the brightest beacons in the entire cosmos, quasars, the luminous hearts of active galaxies, objects we can see clear across the observable universe, are powered by the very things we think of as the darkest. The light is the universe's way of marking where its deepest pits are. And that is why, when astronomers needed something small enough to be a dot and bright enough to be seen at the dawn of time, the feeding black hole was not a wild guess. It was the one object that could plausibly be both. The black hole theory had something the starburst theory had been straining for, a way to be that bright from a single point. One feeding black hole at the centre of a little red dot could account for the tremendous luminosity coming out of that tiny space, with no need to pack in an impossible crowd of stars, and it could account for the point-like appearance too. If essentially all the light is coming from one brilliant central engine, then of course the object looks like a dot. There is nothing else bright enough to see. The central source drowns out the rest, exactly as the second reading of our fork predicted. But what about the redness? The property that has been driving this whole investigation? The black hole theory had an answer for that as well, and it is rather beautiful. Surrounding the accretion disk of a supermassive black hole, astronomers have long known there is often a thick donut-shaped ring of gas and dust. They call it the torus. Now picture the geometry. If you happen to be looking at one of these systems edge-on, peering at it through the plane of that donut, then the thick dusty ring of the torus sits directly between you and the brilliant accretion disk behind it. And what does a thick veil of dust do to light passing through it? You already know. It scatters away the blue and lets the red come through. The torus seen edge-on would redden the black hole's light exactly the way the atmosphere reddens a sunset. So the redness, in this theory, was not a mystery either. It was geometry. It was a matter of viewing angle. That idea, that an object can look like a completely different thing depending on the angle you happen to catch it from, is a recurring and slightly humbling theme in astronomy, and it is worth a moment. We do not get to walk around the objects we study. We see each one from exactly one direction, the single line of sight that happens to connect it to Earth, frozen for the whole of human history, a galaxy with a feeding black hole seen face-on, looking straight down into its bright core, and the same kind of galaxy seen edge-on, peering through the thick dusty torus, can look so different that astronomers once catalogued them as separate species entirely before realizing they were the same thing viewed from two different seats. So when the black hole theory explained the redness of the little red dots as a viewing angle, it was making a reasonable and well-precedented move. Perhaps the dots were simply feeding black holes that we happened to be seeing edge-on through the dust. It was the kind of explanation that had worked before. It deserved its hearing. It simply turned out when the X-rays went looking for themselves and came back with nothing, that geometry was not going to be enough this time, and there was more. The theory kept paying out. Remember the broad emission lines astronomers had seen in the spectra of the little red dots? Broad features smeared out wide across a range of wavelengths. A feeding black hole explains those with ease. Around an active black hole, gas does not sit still. It whirls, orbiting the central mass at staggering speeds, thousands of kilometers every second. And here is the consequence. Some of that orbiting gas on one side of the black hole is sweeping toward you. Some of it on the other side is rushing away. The light from the gas moving toward you gets shifted slightly toward the blue. The light from the gas moving away gets shifted slightly toward the red. And when you add all that orbiting gas together, all those slightly blue and slightly red shifts blended into one signal, the result is a spectral line smeared out, broadened, spread wide. The faster the gas orbits, the broader the line. And broad lines are precisely what a massive black hole feeding hungrily on a lot of gas would produce. The little red dots had broad lines. The theory predicted broad lines. Another match. So take stock of where the black hole theory stood. It explained the brightness. It explained the point source appearance. It explained the redness through the edge on torus. It explained the broad emission lines through orbiting gas. After the collapse of the starburst idea, this felt like solid ground at last. The little red dots, it seemed, were powered by feeding supermassive black holes in the early universe. The case looked strong. It looked for a while close to settled. And then astronomers noticed what was missing. Not something that was there and wrong, something that should have been there and simply was not. Because there is one more thing a feeding black hole reliably does, something so consistent that astronomers treat it as a near certainty. An actively accreting black hole emits X-rays. The superheated gas in the innermost accretion disk, that 12 million degree maelstrom, radiates powerfully in X-rays. It is one of the surest signatures of a feeding black hole in the entire sky. If you have an active, supermassive black hole, you have X-rays. So astronomers went looking for the X-ray glow of the little red dots, fully expecting to find it, to nail the case shut, and they found nothing. No X-rays, not a faint trace, not a weak signal at the edge of detection. The little red dots were X-ray silent. And for a theory built on feeding black holes, silence where there should have been a roar was not a small discrepancy. It was a devastating blow. There was a second problem too, and it cut just as deep. When astronomers estimated the masses of the black holes that would have to be powering the little red dots, those black holes came out far too big. There is, in the universe around us, a remarkably tight relationship between a galaxy and the black hole at its heart. In the nearby present-day universe, a galaxy's central black hole is typically about 0.1% of the mass of the galaxy surrounding it. That ratio holds so consistently across so many galaxies that astronomers believe galaxies and their black holes must grow up together, locked in step by some feedback mechanism that keeps each in proportion to the other. But the little red dots broke that rule. Their black holes came out at something closer to 10% of the galaxy's mass, 100 times more than the universe is supposed to allow. It was as though the black hole had somehow raced ahead and reached its full enormous size before the galaxy around it had even begun to catch up. The astrophysicist Fabio Percucci of the Harvard-Smithsonian Center for Astrophysics summed up the whole maddening situation with a clarity worth repeating. If the little red dots contain black holes, he said, then those black holes are enormous for such small galaxies. But if they only contain stars, then the galaxies are too compact to hold all of them, reaching stellar densities that are unthinkable. Read that again, because it is the trap stated perfectly. Every door is locked. The starburst theory failed on its arithmetic. The black hole theory failed on its missing X-rays and its impossible proportions. Two strong, sensible, well-motivated explanations, and the universe had quietly defeated them both. And that is the moment the little red dot stopped being a puzzle that astronomy expected to solve with familiar tools and became something else, a sign written across the early universe that we were missing something fundamental. The kind of mystery that does not get cleared up by trying harder with the old ideas. The kind that only yields when someone is willing to go looking for it on purpose. Part 7. The Survey That Went Hunting. Up to this point, the little red dots had been found by accident. That is worth saying plainly, because it shapes everything about how the story had gone so far. Eiger and Fresco, the surveys that first turned up the dots, were not looking for them. The dots were a side effect, an uninvited guest noticed in the corners of images aimed at other questions. And there is a real limit to what you can learn about a thing you only ever catch sideways. To truly study the little red dots, to gather enough of them, with enough detail, to actually corner the mystery, somebody would have to stop catching them by accident and start hunting them on purpose. Somebody would have to point the most powerful telescope ever built directly at the strangest objects in the sky and say, "Show me more of these, on purpose and in depth." That somebody was an astrophysicist named Anna de Graaf working at the Center for Astrophysics, Harvard and Smithsonian. And de Graaf was, in a sense, the right person for the job by temperament. Her particular scientific interest was the extreme, the objects that sit furthest outside the expected distribution, the outliers, the ones that do not behave. Most of science, by necessity, studies the typical, because the typical is what the rules are built to describe. But the typical is not where the rules break, and de Graaf was drawn to exactly the places where they break. So she designed a survey to go straight after the strangest thing she could find. She gave it a fitting name, the Rubies survey, the letter standing for Red Unknowns, Bright Infrared Extragalactic Survey. Read that name slowly, because it is almost a mission statement in itself. Red unknowns. Not red galaxies, not red quasars. Red unknowns, things whose very category was undecided. Bright, infrared, extragalactic. Rubies was a deliberate, targeted hunt for the reddest, brightest, rarest objects in the entire sky. It was science walking with its eyes open directly toward the thing it could not explain. And there is something quietly admirable in that. It would be easier and safer for a career to study the things that behave. De Graaf built a survey to chase the things that do not. That choice is worth honouring, because it runs against a quiet pressure that shapes a great deal of science. Telescope time is scarce and fiercely contested, and the safe way to win it is to propose a study of something the committee already understands. A project with a predictable result, a guaranteed paper, a tidy outcome. Proposing instead to spend 60 hours of the most valuable telescope in existence, chasing objects whose very category is undecided, objects you cannot promise will resolve into anything at all, is a genuine professional risk. It is staking a precious resource on a question that might simply refuse to answer. But the history of discovery is, overwhelmingly, the history of people who took that risk, who pointed the best instrument of their age not at the reassuring centre of what was known, but at its strange and stubborn edge. The little red dots were never going to be understood by accident, in the corners of images aimed elsewhere. Somebody had to decide they were worth a deliberate hunt. Rubies is what that decision looked like, and the rest of tonight's story exists because someone was willing to chase the things that do not behave. During 2024, de Graaf and her team were granted nearly 60 hours of precious James Webb observing time. And observing time on Webb is one of the most contested resources in all of science, fought over by astronomers across the world. They spent those 60 hours obtaining spectra, not just images but full spectral fingerprints, for 300 red sources. And of those 300, the team estimated that somewhere between 30 and 50 were the genuine, mysterious little red dots. When the work was published, in March 2025, it was the largest spectroscopic sample of little red dots ever assembled. For the first time, astronomers were not squinting at one or two accidental dots. They had a real population in hand, with real fingerprints, spanning a stretch of cosmic time from 650 million to 1.5 billion years after the Big Bang. De Graaf had gone hunting, and she had come back with a catalogue. And here is what you might reasonably hope happens next. You might hope that a survey this deliberate, this large, this carefully done would finally bring some order, some calm, some clarity, that with 30 to 50 proper spectra in hand, the little red dots would resolve into a clear answer and the field could exhale. That is what de Graaf hoped for too, and it is of course the opposite of what happened. What Rubies revealed was that the little red dots, far from being one clean type of object, were a far more diverse and tangled population than anyone had imagined. When you only have images, objects that look alike get filed together, but spectra cut deeper. Spectra read the fingerprints, and the spectra showed that the things lumped together under the label little red dots were, in truth, several different kinds of object wearing a similar coat. Some of them really were dusty galaxies, still busily forming stars. Some appeared to be galaxies that had, surprisingly, already stopped forming stars. Quenched, shut down, far earlier in cosmic history than that was supposed to happen. And some were active black holes powering the bright cores of galaxies. So in a strange way, both sides of the long argument, the starburst camp and the black hole camp, turned out to be partly right. The little red dot label had been a bucket, and the bucket held several different things. It is worth pausing on how genuinely useful that finding was, even though it was not the answer. There is a temptation, when a long argument finally gets resolved, to keep score, to ask which camp won, the starburst astronomers or the black hole astronomers. But Rubies delivered a subtler and better result than a winner. It said both camps had been looking at real things, and both had been overgeneralizing from them. The starburst astronomers really had been seeing dusty star-forming galaxies among the little red dots. They existed. The survey confirmed it. The black hole astronomers really had been seeing active black holes among the little red dots. They existed too. The mistake on both sides had not been bad observation. It had been the assumption that the little red dots were a single kind of thing, so that whatever you found in a few of them must be the explanation for all of them. Rubies broke that assumption. It showed that the label had been doing too much work, gathering several genuinely different objects under one name simply because they looked alike in a photograph. And that is a real advance, because a mystery you have correctly divided is a mystery you can finally make progress on. As long as the little red dots were one undifferentiated puzzle, every new observation seemed to contradict every other one, because astronomers were, without knowing it, comparing measurements of different objects and expecting them to agree. Once Rubies separated the dusty galaxies and the ordinary active black holes and set them aside, the contradictions in the leftover subset stopped being noise and started being signal. The remaining objects genuinely did all share the same stubborn properties. They genuinely did defy explanation in the same way. The survey had not solved the mystery, but it had done something almost as valuable. It had purified it. It had taken a blurry, mixed, half-real puzzle and handed back a smaller, sharper, entirely real one. The hard core of nameless objects that the black hole star would, in the end, be invented to explain. It would have been tempting to call that the answer, to say, mystery solved, the little red dots were never one thing, they were a mixed bag, and now we have sorted the bag. But de Graaf and her team were too careful for that, and the data would not have let them get away with it anyway. Because within that diverse population, after the dusty galaxies and the quenched galaxies and the ordinary active black holes had all been identified and set aside, there was a subset left over. A hard core of objects that fit none of the categories, none of them. These were the dots with the full stubborn signature, the V-shaped spectrum, the broad emission lines, the point source compactness, the whole maddening package that had resisted every explanation from the very beginning. Rubies had sorted the bucket, and at the bottom of the bucket there was still something that did not have a name. So the survey that was meant to bring clarity did something better and harder. It separated the genuine mystery from the noise. Before Rubies, the little red dots were a vague, blurry puzzle, partly real strangeness, partly just a mix of ordinary things seen badly. After Rubies, the ordinary things had been peeled away, and what remained was a smaller, sharper, and far more concentrated mystery. A specific subset of objects well observed that genuinely matched nothing in the catalogue of known cosmic things. The hunt had not caught the answer, but it had cornered the question, and papers by now were beginning to pour out of the field faster than anyone could read them, the sign of a science that knows it is standing next to something important. Hold that detail too, the flood of papers. It will return at the very end of the night, and it will mean something then. For now, the cornered question was about to get a face, because within that leftover subset of nameless objects there was one, a single dot in a single spectrum, so extreme that when it appeared on a screen, it stopped an entire research team where they sat. Part 8. The Cliff. It is July of 2024. Picture the room, because the room is real, even if the details are ordinary. A workspace, screens, the quiet hum of a research group going through data. The Rubies team is doing what survey teams do, the slow and patient work that almost never makes the headlines. Processing spectra, one red source after another, turning raw telescope data into clean, readable fingerprints of light. It is methodical work. Most of it produces another reasonable data point, another object that more or less behaves, another entry for the catalogue. That is what a survey is, most of the time. Expectation, confirmation, the next file. And then one particular object's spectrum finishes processing and resolves on the screen, and it does not behave at all. The feature that stops them is the Balmer break, that sharp step in the spectrum we spent time understanding earlier, the cliff edge that marks where hydrogen stops letting light through. Every little red dot they had studied showed a Balmer break of some kind. But this one's break is not a step. It is a wall. It is near vertical, brutally sharp, and it is roughly twice as strong as the Balmer break of any ancient cosmic object ever observed before it. Twice as strong as anything. In a field where you fight for incremental improvements, where a result that is 10 or 20% beyond the previous record is worth celebrating, here is a feature that doubles it. The team looks at that near vertical edge on the screen, and they understand in that moment that they are not looking at another data point. They are looking at something that does not fit, and is not going to be made to fit. They gave it a name that matched what they saw. They called it the Cliff. The Cliff is a little red dot roughly 11.9 billion light-years away. Its light set out when the universe was a small fraction of its current age. And the reason it stopped the team cold is not just that its Balmer break was extreme. It is that the cliff was sending two messages at once, and the two messages contradicted each other. On one hand, the broader analysis of its spectrum pointed toward a supermassive black hole, the signatures of a feeding monster at the centre. On the other hand, that dramatic near-vertical Balmer break pointed towards something else entirely. Remember what a sharp Balmer break means. Not just hydrogen, but a great deal of remarkably pure, remarkably uniform hydrogen gas. The kind of smooth, even atmosphere of hydrogen you would associate with a very young star, not with the chaotic environment around a black hole. The cliff looked like a black hole, and the cliff looked like a young star. At the same time, in the same object, from the same light. That is not supposed to be possible. A black hole and a young star are different things, governed by different physics, and an object is meant to be one or the other. The cliff was refusing to choose, and when a single object refuses to choose between two categories that are supposed to be mutually exclusive, a careful scientist is left with only one honest conclusion. The categories themselves might be wrong, or rather, incomplete. There might be a kind of object the categories had simply never included, because nobody had ever needed to. Anna de Graaf put it directly. The extreme properties of the cliff, she said, forced us to go back to the drawing board and come up with entirely new models. Sit with that sentence for a moment, because of how rarely a scientist gets to say it and mean it. Back to the drawing board is not a casual phrase here. It means the existing toolkit. Every model of stars, every model of galaxies, every model of black holes that astronomers had brought to bear on the little red dots, had been laid out, tried, and found wanting. It means the failure of the starburst theory and the failure of the black hole theory were not two separate stumbles to be patched independently. They were a single, deeper signal. The framework itself was missing a piece. The cliff was the object that made that undeniable. One dot, one spectrum, 11.9 billion years old, and sharp enough to cut through every assumption the field had carried into the problem. There is a particular feeling in science when this happens, and it is not the dismay you might expect. It is closer to a kind of vertigo, and underneath the vertigo something almost like exhilaration. Because a result this stubborn is not a dead end. It is a door. It is the universe declining to fit inside your existing ideas, which means your existing ideas were too small, which means there is something larger and truer waiting just past them. The team that processed the cliff spectrum that day in July was not looking at a problem. They were looking at an invitation. Let the scene hold for one more moment, because moments like it are rarer than the headlines suggest, and this one deserves to be felt rather than summarized. Most days in a working science are days of small, patient progress, a measurement refined, a model nudged, a catalogue grown by one more entry. The dramatic break, the discovery that genuinely overturns the table, is something most researchers experience only a handful of times in an entire career, if at all, and it almost never arrives looking like triumph. It arrives looking like a mistake. The first honest reaction to the cliff spectrum would not have been delight. It would have been suspicion, a quiet, sinking certainty that something in the instrument had gone wrong, that the calibration had slipped, that the data needed to be run again. That is the proper response, and you can be sure the Rubies team did exactly that. Checked and rechecked and tried to make the strangeness go away. And the strangeness did not go away. The cliff held. The near-vertical break was real, twice as steep as anything in the record, and it was not an error, and it was not going to become one no matter how many times they looked. There is a particular silence that follows that realization, the point where you stop trying to explain the result away, and start to understand that the result is explaining something to you, the point where the question quietly flips. From what did we do wrong to what is the universe doing that we never imagined? That silence, in that room, in July of 2024, is where the black hole star was really born. Not in a flash of insight, but in the slow, reluctant, honest admission that the old playbook had nothing left to offer, and that something new would have to be invented to make a single small red dot, 11.9 billion years away, finally make sense. The old playbook had been thrown out openly by the data itself, and the question now was no longer how do we fit the little red dots into what we know. The question was, What new kind of object would have to exist for the cliff to make sense? What could possibly be a black hole and a star at the same time? De Graaf had an answer. It was strange enough to sound like something out of science fiction, and it was about to turn out to have been quietly waiting in the scientific literature for 16 years. Part 9. The object that is both. Here is the idea, and I want you to let it sound as strange as it is, because the strangeness is the point. This is genuinely a new kind of object being proposed, not a small adjustment to an old one. De Graaf's answer to the cliff, to the V-shaped spectrum, to the broad lines and the missing X-rays and the impossible proportions, was that the little red dots in that stubborn leftover subset are neither starburst galaxies nor ordinary active black holes. They are a third thing. An object that is, in a real and physical sense, both a black hole and a star at once. She gave it a name as plain and as startling as the little red dots themselves. She called it a black hole star. A black hole star has, as the name promises, the characteristics of both. From the outside, it looks like a star, or at least, it looks like the thing we most associate with a star, which is a vast glowing sphere of hot, dense gas. A black hole star is shrouded in exactly that, an enormous envelope of hot hydrogen, so large and so luminous that, viewed from a great distance, it presents the smooth, glowing face of a stellar atmosphere. If you only saw its outer layer, you would file it without hesitation as a star. But a black hole star does not run the way a star runs. An ordinary star, our Sun, every star you can see tonight, is powered by nuclear fusion in its core, hydrogen atoms forced together to make helium and release energy. A black hole star has no such core. At its centre, instead, there is a supermassive black hole, and that black hole is feeding, accreting matter at tremendous speed, devouring the dense gas around it, converting that matter into energy and releasing light. The glow of a black hole star is not the glow of fusion. It is the glow of a black hole eating, a star-shaped object lit from within by the one thing in the universe we think of as the opposite of a star. Now, a strange idea is cheap. Anyone can propose a strange object. What makes the black hole star worth taking seriously, what lifts it from science fiction to science, is that it does the one thing the starburst theory and the ordinary black hole theory could not. It explains the evidence. All of it. Not 3 of the 4 problems with a shrug at the 4th. All of it in a single coherent picture. Let me walk you through how, because this is the moment the night's mystery starts, genuinely, to resolve. Start with the missing X-rays, the devastating blow that killed the ordinary black hole theory. Recall the problem: a feeding black hole should pour out X-rays, and the little red dots emit none. The black hole star answers this not by claiming the X-rays are absent, but by claiming they are trapped. In a black hole star, the central black hole really is feeding, and it really is generating X-rays, exactly as a feeding black hole should. But that black hole is buried at the heart of an immense, dense envelope of hydrogen gas, and that envelope is so thick, so opaque, that even high-energy X-rays cannot punch their way out of it. The X-rays are produced, and then they are absorbed by the surrounding gas before they can ever escape into space. They do not vanish. Energy cannot simply vanish. They are absorbed and re-emitted and degraded, step down into lower energy light, into the thermal glow and the red optical light that we actually see. The missing X-rays were never missing. They were swallowed by the object's own atmosphere and handed back to us as red light. The X-ray silence is not the absence of a black hole. It is the fingerprint of a black hole wearing a very thick coat. And notice what kind of solution that is, because it is a particular and telling kind. The ordinary black hole theory had treated the missing X-rays as a fatal contradiction. The data said no X-rays, the theory said there must be X-rays, and a flat contradiction kills a theory. But the black hole star does not argue with the data. It accepts the observation completely. There really are no X-rays reaching us. It simply adds one piece of structure, a dense envelope, that turns the absence into a prediction. A bare feeding black hole should show X-rays, yes, but a feeding black hole buried inside a thick enough shroud should show none, because the shroud eats them. The black hole star did not have to deny what astronomers saw. It had to explain why what they saw was exactly what this new kind of object would produce. That is the difference between a theory that is merely rescued and a theory that is genuinely better. The first explains away an inconvenient fact. The second turns the inconvenient fact into evidence in its own favour. Now, the dust shortfall, the arithmetic that killed the starburst theory, Casey's team had found only 1% of the dust needed to explain the redness. The black hole star dissolves that problem in the most elegant way imaginable. It says there is no dust to account for. Under the black hole star model, the little red dots contain essentially no dust at all. They never needed it. The redness was never caused by dust in the first place. It is caused by the dense hydrogen envelope itself, by the sheer opacity of that thick shroud of gas, which reddens the light passing through it from the feeding black hole at the core. And once you remove dust from the explanation entirely, the dust shortfall stops being a problem. You cannot have a shortage of something you do not need. The 100-fold gap that doomed the starburst theory simply ceases to exist. And then the overmassive black hole problem, the black holes that came out 100 times too big for their galaxies. This one is the most subtle and the most satisfying, because the black hole star does not just excuse the problem, it explains why we were fooled. Remember how astronomers weigh a distant black hole? They cannot put it on a scale. What they do instead is measure the breadth of its emission lines, the width of those smeared out spectral features. The logic is sound. Broader lines mean faster moving gas, and faster moving gas means a stronger gravitational grip, which means a more massive black hole. Broaden the lines, raise the mass. It is a standard, trusted technique. But it carries a hidden assumption. It assumes the light travels cleanly outward from the gas to your telescope, picking up no extra broadening on the way. In a black hole star, that assumption fails. The light does not travel cleanly outward. It has to fight its way out through that immense, dense hydrogen envelope, and on the way the photons collide. They scatter, bounce off the gas again and again and again, ricocheting through the thick shroud before they finally escape. And every single one of those collisions shifts the photon's wavelength just slightly. Add up millions of those tiny shifts, accumulated over a tortured path out through the envelope, and the effect is to smear the emission lines wider, to broaden them well beyond what the central black hole's gravity alone would produce. So astronomers measured very broad lines, applied the standard technique, and calculated very large masses. But a large fraction of that line width was never gravity at all. It was photon scattering. It was the envelope, not the black hole. When researchers corrected for this, when they accounted for the scattering and stripped out the broadening the envelope had added, the estimated black hole masses dropped, not by a little, but by orders of magnitude, by a factor of something like 100 to 300, and the corrected masses fell back into line, back toward that familiar 0.1% ratio we see in the calm universe around us. The black holes were never too big. We had simply been weighing the coat along with the body. That leaves the V-shaped spectrum, the strange double-peaked signature, strong in the blue and the red and sagging in the middle, that matched nothing in the catalogue. And here the picture widens thanks to work by the astronomer Rohan Naidu and his team at MIT. In 2025, studying a related object, Naidu's group found a thick envelope of hydrogen gas about 40 astronomical units across, 40 times the distance from the Earth to the Sun, and one of the strongest Balmer breaks ever recorded at any distance in the universe. And Naidu argued that to understand the V-shape you should think of the whole thing as a two-part object. There is the black hole star itself, and that component produces the broad emission lines, the strong Balmer break, the compact point-like glow, and the powerful red light. And then there is a host galaxy surrounding it, an ordinary star-forming galaxy, and that component produces narrow emission lines in the ultraviolet. Now layer those two together, the low-energy red light from the black hole star at the centre, and the high-energy ultraviolet light from the star-forming galaxy around it, both reaching your telescope at once, superimposed into a single spectrum, a strong red side, a strong blue side, and a dip in the middle where neither component contributes much. That is the V. The V-shaped spectrum was never one impossible object. It was two ordinary enough things seen together, and once you know to look for both, the strangeness resolves into sense. Let me take you inside one. Close your eyes, if they are not closed already, and travel to a black hole star in the early universe. You approach it through the dark, and at first it is exactly what its outer appearance promised. A vast glowing sphere, the warm red-gold face of what looks for all the world like an enormous star hanging in the young cosmos. But now sink inward, downward, through that glowing surface and feel the gas thicken around you. This is the hydrogen envelope. It is dense beyond anything in an ordinary star's atmosphere, and it is huge. Tens of astronomical units of it. A shroud you could lose whole solar systems inside. And it is restless. Everywhere around you, light is struggling. Photons born deeper in are trying to climb out, and the gas will not let them pass cleanly. They scatter and scatter again, each collision nudging them a little redder, so that the light itself seems to wander, lost, taking thousands of crooked steps for every honest one. Somewhere in here, the X-rays are dying, high-energy light snuffed out in the murk, its strength absorbed and handed downward into a softer, redder glow. And then you reach the centre, and the centre is not a core of fire. The centre is a supermassive black hole, silent and enormous, feeding on the dense gas that presses in around it, turning matter into the energy that lights the whole vast sphere from within. You are standing, if you could stand, inside a star that has no star in it, just a black hole, and its enormous swallowed breath of hydrogen, glowing in the dark of the first billion years. Stay inside it for one moment longer, because it is worth understanding just how thoroughly a black hole star confounds the simple picture of the cosmos we carry in our heads. We are taught early that the universe sorts itself into clean kinds of things. Stars are one kind of thing, balls of gas lit by fusion shining. Black holes are another kind of thing, pits in space-time, dark, defined by what cannot escape them. The two are presented as opposites, the lit and the unlit, the giving and the taking, the thing that pours light out and the thing that lets nothing out at all. And for the great majority of the universe, that tidy division holds perfectly well. But the black hole star sits exactly on the seam between the two categories and refuses to fall to either side. From the outside, by every signal that reaches a distant telescope, it is a star, a vast glowing sphere, warm and red and luminous. From the inside, at its core, it is the purest example of the opposite thing, a feeding black hole, the very emblem of darkness and swallowing. It is not a star pretending to be a black hole, and it is not a black hole pretending to be a star. It is genuinely and physically, both at once, a black hole that has clothed itself in the glowing body of a star, and shines, paradoxically, on the strength of its own appetite. That is why the object is so much more than a clever fix for an awkward spectrum. It is a reminder that the universe's categories are ours, not its. We sorted the cosmos into stars and black holes because that sorting was useful, and for a long time, complete enough. The little red dots are the universe quietly informing us that the sorting was never the whole truth, that there is at least one kind of object that lives in the gap between our boxes, and that it was not rare or marginal but abundant, filling an entire early epoch, while we simply lacked the eyes and the imagination to know it was there. That is the black hole star. One strange idea, and it quietly pays off 4 separate debts that the sensible ideas could not. The X-rays, the dust, the overmass, the V-shape, all of it explained in a single picture. And that is exactly how a real discovery tends to announce itself. Not with one lucky match, but with a strange new idea that, once you accept it, makes a whole crowd of unrelated problems fall silent at the same time. The little red dots had defeated every familiar explanation, and the explanation that finally held was not familiar at all. It was an object nobody had ever seen. A black hole wearing the body of a star. But a black hole star, if it is real, cannot simply appear. It has to be built. Something in the early universe had to assemble it, and to understand how, we have to leave the object itself and look at the invisible scaffolding the whole cosmos is hanging on. Part 10. Born in the slowest halos. Every structure in the universe, every galaxy, every cluster of galaxies, every little red dot, sits on a foundation you cannot see. We have spent this whole night talking about light, red light, blue light, X-rays, the fingerprints in spectra. But the framework that decides where all that light gets built is not made of light at all. It is made of dark matter. And to understand where a black hole star comes from, you have to picture that framework first. Dark matter does not shine, does not absorb light, does not interact with the ordinary stuff of the universe in any of the ways that would let us see it directly. But it has mass, and mass has gravity, and gravity is something we can map. And when astronomers map it, what they find is that the universe is threaded through with an immense invisible architecture, vast structures of dark matter called halos, strung together in a sprawling interconnected web. It is one of the most beautiful images in modern cosmology, and a slightly eerie one. If you could see the dark matter web of the universe, it would look strikingly like the network of neurons in a human brain. Filaments, nodes, and connecting threads, a cosmic web branching across hundreds of millions of light years. We cannot see it with our eyes, but we can map it using a technique called gravitational lensing, watching how the gravity of the invisible halos bends the light of more distant objects passing nearby, and reading the dark matter's shape from the distortions. And the map tells us something crucial. The dark matter halos are where galaxies form. The halos are the scaffolding. Ordinary matter, gas, the raw material of stars and black holes, falls into the halos, pools there, and goes to work. Where there is a halo, there can be a galaxy. The web is the blueprint of cosmic structure. But here is the detail that matters for the little red dots. The halos spin, and they do not all spin at the same rate. Most dark matter halos spin relatively fast, and when a halo spins fast, it has a consequence for the gas that falls into it. The spin flings that gas outward. Think of a carnival ride, the kind that whirls you in a circle. The faster it spins, the more you are pressed outward, the further the swings ride out from the centre. A fast-spinning halo does that to its gas. The gas spreads out, thins, disperses across a wide region, and spread-out gas builds a spread-out thing, an ordinary galaxy, broad and structured, with its material distributed across tens of thousands of light-years. That is the normal story. That is how most of the galaxies in the universe, including our own, got their gas arranged. But a small fraction of halos, a rare minority, spin extremely slowly. And in a slow-spinning halo, the carnival ride is barely turning. There is almost no outward fling, so the gas that falls in does not spread. It stays where it lands, dense, compact, concentrated, pulled tightly at the centre instead of flung wide. And that changes everything about what can be built there. A slow-spinning halo gathers its gas into a small, dense, concentrated reservoir, exactly the kind of environment that does not make an ordinary sprawling galaxy at all. It makes something compact, something with a great deal of dense gas packed into a tiny volume. It makes, astronomers now think, the cradle of a black hole star. Let me take you there too, because it is a quieter scene than the inside of the black hole star and worth seeing. Picture yourself floating above the cosmic web in the early universe, the vast, dark neural network of halos stretched out below you, glimmering not with light but with the gravity you have learned to read. Watch the gas moving through it. Around most of the halos, the gas is in motion, spinning, flinging itself outward, spreading into the broad disks that will become galaxies. There is a kind of restlessness to it, matter racing outward everywhere you look. But now, find one of the rare ones, one of the slow halos. Settle onto it and feel how different it is. Here the spin is almost nothing. Here the gas is not racing anywhere. It falls inward and it simply stays, gathering, thickening, pooling into a dense and patient knot at the centre, undisturbed. There is a stillness to a slow halo that the rest of the web does not have. And in that stillness, in that quiet, dense pocket of concentrated hydrogen, something begins to take shape, a seed at the centre and a vast reservoir of gas around it, ready to be devoured and ready to glow. You're watching the conditions for a black hole star assemble out of almost nothing, out of the simple accident of a halo that happened not to spin. There is something quietly profound in that phrase, the simple accident of a halo that happened not to spin, and it is worth resting on before we move on. We like our cosmic stories to have grand causes. We like to imagine that something as significant as the seed of a supermassive black hole must require some grand and special trigger, some rare cataclysm, some deliberate cosmic engineering. But the slow halo picture says something humbler and stranger. It says that one of the most consequential objects the universe can build may depend at bottom on a roll of the dice, on a halo that, for no dramatic reason at all, simply drew a low number for its spin. Most halos spin fast and make ordinary galaxies. A few spin slow, and in those few, the gas stays dense, and density is destiny. The little red dots on this picture are the universe's lucky pockets, the rare quiet corners of the cosmic web where the conditions happen to line up. And that has a consequence for the question we keep circling. Why do the little red dots vanish? Part of the answer, as we'll see, is about time and the supply of gas, but part of it is simply rarity. Slow spinning halos were always a minority. The conditions for a black hole star were always a fine and unlikely balance. Enough gas concentrated enough in a halo calm enough to let it stay concentrated. Fine balances do not last. As the universe ages and stirs and spreads its material out, the particular stillness a black hole star needs becomes harder and harder to find. The little red dots were never going to be a permanent feature of the cosmos. They were a brief alignment of unlikely conditions, and the wonder is not that they ended. The wonder is that the universe held that fragile balance long enough, often enough, to fill an entire early epoch with them. So the formation story has a shape now. Rare, slow-spinning halos, gas that stays dense instead of dispersing, and in that density the raw material to build a black hole at the centre and wrap it in the enormous hydrogen envelope that gives the black hole star its name and its strange double nature. It is a satisfying picture, but it raises an obvious and pressing question, the kind a careful listener should be asking by now. This is a brand new idea. Black hole stars, born in slow halos. We have only just been forced into it in the last couple of years by the cliff and by Rubies and by the stubborn data. So how new is it, really? Did the universe wait until 2024 to be understood? Or is it possible that someone, somewhere, had already imagined this object, had seen it coming, in the pure abstract language of theory, long before any telescope could catch one? The answer is the most remarkable turn in the entire story. Because the black hole star was not invented in 2024, it was predicted, 16 years earlier, by one man working it out on paper with no way on earth to know whether he was right. Part 11. The Prediction. From 2008. In 2008, a theoretical astrophysicist named Mitchell Begelman, working at the University of Colorado, published a paper. There was no James Webb Space Telescope then. It would not launch for another 13 years. There were no little red dots because nobody had the instrument to see them. There was no cliff, no Rubies survey, no V-shaped spectrum sitting unexplained on anyone's screen. There was just Begelman, and the physics, and a question he was working through with mathematics. What happens if a black hole forms inside a dense enough cloud of gas? The object he described, he called a quasi-star. And if you have been listening closely tonight, the description is going to give you a quiet chill of recognition. Begelman's model went like this. Imagine a black hole forming, from a stellar remnant or from some small seed, but forming inside a cloud of gas so dense that the gas does not get blown away. In the ordinary story, a young black hole's surroundings disperse, but Begelman asked, what if they do not? What if the envelope of gas stays gravitationally bound, held in place, wrapped around the black hole instead of scattering? Then you would have a black hole sitting at the core feeding on the gas around it, and the outer envelope of that gas would glow, not from nuclear fusion, the way a real star glows, but purely from the energy of the black hole devouring matter at the centre. From the outside, Begelman wrote, such an object would look like a single enormous star, but inside it would be a black hole. He called it a quasi-star. We have spent tonight calling the same object a black hole star. They are the same idea. Begelman simply had it 16 years early, and his model did not stop at the picture. It made predictions, specific, quantitative predictions about how such an object would behave. Begelman calculated that a black hole in this configuration, swaddled in dense gas and feeding hard, could grow at an extraordinary rate. It could reach thousands of times the mass of our Sun in just a few million years, which on the cosmic clock is the blink of an eye. The envelope, meanwhile, would slowly cool, and eventually it would reach a kind of floor, a temperature of around 4,000 Kelvin, below which it could not be sustained. At that point, the balance tips. The radiation pressure from the feeding black hole wins out over the gas's ability to hold together, and the envelope is blown away. The quasi-star phase ends, and what is left behind, naked now with its coat stripped off, is the black hole itself. Notice what that means. Begelman was not describing a permanent type of object. He was describing a phase, a chapter in a black hole's life, brief and early and dramatic, lasting only a few million years before the envelope disperses and the phase is over. The quasi-star is not a thing a black hole is. It is a thing a black hole goes through, And Beagleman even suggested, looking further down the line, that if a black hole later ran into another episode of extremely heavy gas inflow, another dense feast, the same conditions could arise again. A black hole might pass through a quasi-star phase more than once across its long life, and that idea that the quasi-star is a phase requiring very particular conditions quietly answers a question we left hanging all the way back at the start of the night. Remember the strangest property of the little red dots, that they switch off, that they crowd the early universe around 600 million years after the Big Bang and are simply gone by 1.5 billion years. For a long time in this story, that vanishing had no explanation, but look at it now through Beagleman's model. If a black hole star is a phase, and that phase needs the specific condition of extreme gas inflow into dense concentrated reservoirs, then it follows naturally that black hole stars can only form while the early universe is still supplying those conditions. And the early universe will not supply them forever. As cosmic time goes on, the gas gets used up, spread out, settled down. The dense, heavy inflows that feed a quasi-star become rare and then absent. The window closes. The little red dots do not die out because something kills them. They cease because the universe stops being the kind of place that makes them. The vanishing was never a separate mystery. It was Beagleman's model, quietly predicting itself. There is a deep satisfaction in a moment like that, and it is worth naming, because it is one of the surest signs that a theory is on the right track. When the little red dots first appeared, every one of their strange properties looked like a separate problem. The compactness was one puzzle, the brightness was another. The redness, the V-shaped spectrum, the missing X-rays, the overmassive black holes, the vanishing. Each one seemed to demand its own explanation, and a starburst theory or a black hole theory could, at best, account for some of them while leaving the rest as loose, unexplained ends. But a genuinely good model does something different. It does not solve the puzzles one at a time. It reframes the whole picture so that the puzzles solve each other. The black hole star did exactly that. Accept the dense envelope and the X-rays explain themselves, and the dust shortfall explains itself and the overmass explains itself. Accept Beagleman's idea that the object is a phase requiring particular conditions, and the vanishing explains itself too, not as a new mystery bolted on, but as a straightforward consequence of an idea you already adopted for entirely different reasons. That is the texture of a real explanation. The loose ends stop being loose. The thing you invoke to solve problem 1 turns out, without any further effort, to also solve problems 2 and 3 and 4. And when a model starts paying dividends you did not ask it for, when it answers questions you had not yet thought to put to it, that is the universe's quiet way of suggesting you may have found something true. The black hole star has not been confirmed. We will be honest about that before the night is done. But it has this particular and persuasive quality, the quality of an idea that keeps quietly settling debts it was never handed. The vanishing of the little red dots was a debt nobody handed it, and it settled that one too. Now I want you to sit for a moment with what this actually is, because this is the emotional centre of the whole story, and it deserves to be felt and not just noted. A man sat down in 2008 with no telescope capable of testing him, no data, no image, nothing but physics and mathematics and his own careful reasoning. And he described in detail an object that the universe would not reveal for another decade and a half. He gave it a structure, he gave it a growth rate, he gave it a temperature floor and a lifespan and an ending. He described, essentially, the thing that astronomers in 2024 and 2025 would be stunned to find scattered across the dawn of the cosmos and would feel they were discovering for the first time. Beagleman had been there already, alone, with a pencil. It is worth being precise about what that actually took, because the phrase "a theorist worked it out on paper" can make the achievement sound easier and lonelier than it was. Beagleman was not guessing. He was not sketching a pleasant possibility and hoping. He was doing the hardest kind of physics there is, taking the known, tested laws of gravity, of gas, of radiation, of how matter behaves under extreme pressure and heat, and following them rigorously into a regime where no observation could yet check him. He had to ask what a black hole would do inside a dense cloud, and then he had to let the equations answer honestly, even when the answer was a strange object with no name and no precedent. He had to trust the physics more than he trusted his own intuition about what the universe ought to contain, and he had to be willing to publish the result, to put a strange, untestable object into the scientific record and attach his name to it, knowing it might be decades before anyone could say whether he was right, and knowing that he might simply be wrong on the record forever. That is a particular kind of courage, and it is not the loud kind. It is the courage of taking an idea seriously enough to follow it all the way to its strange conclusion, and then standing behind it in the quiet. For 13 years after that 2008 paper, the quasi-star sat in the literature as exactly that, a careful, rigorous, untested idea, the kind of thing a field files under interesting if true, and mostly leaves alone. Begelman did not get a telescope to vindicate him on a schedule. He got the long wait. And then, 16 years on, a machine a million miles from Earth started sending home images of the dawn of the universe. And scattered through those images were objects that a population of astronomers, stunned, would slowly realize matched a description that had been sitting in a journal the whole time. This is the thing to carry with you into sleep tonight, more than any single number or name. The universe is vast and old and mostly unknown, and it can feel sometimes as though understanding it is beyond what minds like ours could ever manage. And then you remember Begelman, and the pencil, and the 16 years. A human being, working with nothing but known physics and the discipline to follow it honestly, described a real object before the universe was ready to show it to anyone. That is not a small thing. That is one of the quiet glories of what we are, that careful thought, done with enough honesty, can run ahead of sight itself and be standing there waiting correct when the ancient light finally arrives. There is a particular kind of awe that has nothing to do with size or distance or cosmic violence, and this is it. It is awe at the reach of a human mind. The universe did not whisper the quasi-star to Mitchell Begelman. He reasoned his way to it, forward from known physics, and arrived at a real object before the instrument existed to confirm it was real. And think of what that means about the rest of physics, about the strange, abstract theories being worked out on paper right now, tonight, in offices around the world by people the public will never hear of. Some of those ideas, too, are probably descriptions of things we have not yet built the eyes to see. Begelman's quasi-star is not just an explanation for the little red dots. It is a piece of evidence. Evidence that careful thought, done well, can run ahead of observation by 16 years and still be standing there, correct when the light finally arrives. And the light in this case had one more thing to show us. Because the little red dots are not only a mystery solved, they may be the answer to a far older and far deeper question, a question about where the giants came from. Part 12. The first chapter, written in real time. To see why the little red dots matter beyond their own strangeness, we have to talk about one of the deepest unsolved problems in all of astrophysics, and it is this. Where did the supermassive black holes come from? We know they exist. There is a supermassive black hole at the centre of nearly every large galaxy in the universe, including, as you sit there in the dark, the one at the centre of the galaxy you live in. The Milky Way has its own, a black hole of about 4 million solar masses, anchoring the whole slow turn of our 400 billion stars. Supermassive black holes are everywhere. They are a basic feature of how the universe is organised. That part is not the mystery. The mystery is the timing. Because when astronomers look back into the early universe, they find that some supermassive black holes were already there, already grown to billions of times the mass of the Sun, just a few 100 million years after the Big Bang. And that should not be possible. The conventional way to build a black hole is for a massive star to collapse, leaving a black hole seed of perhaps 10 to 100 solar masses, which then feeds and grows. But growing from 100 solar masses to billions takes time, and the early universe simply had not had enough of it. The giants were there too soon. It is as though you walked into a room and found a full-grown oak tree where, by every rule you know, there had only been time for a sapling. And this is not a small or technical embarrassment that astronomers would prefer not to mention. It is one of the genuine load-bearing problems of modern cosmology, the kind of problem that careers are spent on and conferences are organised around. We have a detailed, well-tested, broadly successful account of how the universe grew up, how the first structures formed, how galaxies assembled, how the cosmos came to look the way it does. And sitting inside that successful account is this stubborn splinter. The earliest giant black holes are there too soon, and the standard pathway cannot, by its own arithmetic, have built them in time. A splinter like that is not a reason to throw out the whole account, but it is a reason to suspect that something is missing, that there is a chapter in the story of cosmic structure that we have not yet read, a process the early universe was running that we have not yet identified. For years, that missing chapter had no good candidate. The timing problem was simply a known wound in the theory, acknowledged and unhealed. What makes the little red dots matter beyond their own strangeness is that they arrive carrying something the timing problem has lacked for a long time, a real, physical, observable suspect for the missing process. This is where the little red dots and the black hole star step out of their own story and into a much larger one, because the black hole star model offers a way out of this paradox, and it works on two fronts at once. The first front we have already met tonight. Remember how photon scattering in the dense envelope broadens the emission lines and makes astronomers overestimate the black hole's mass by a factor of something like 100 to 300. Now turn that correction loose on the timing problem. If we have been systematically overestimating the masses of early black holes, then the early universe never had to build objects quite as monstrous as we thought, quite as fast as we thought. Some of the impossible speed was an illusion of measurement. The paradox eases, and the second front is deeper still. Black holes have a natural speed limit on how fast they can feed. It is called the Eddington limit, and it comes from a simple tug of war. As a black hole accretes matter, that infalling matter heats up and radiates, and the pressure of that radiation pushes back outward against the next wave of infalling gas. Feed too fast, and your own light blows your meal away. The Eddington limit is the ceiling. It is one of the main reasons the timing problem is a problem. Black holes are supposed to be throttled. But here is what the black hole star changes. The Eddington limit depends on what is doing the pushing and what is being pushed. And a black hole star is not a bare black hole. It is a black hole wrapped in an enormous, massive envelope of gas. When you wrap a black hole in that much dense material, the calculation of the limit shifts. It is no longer set by the mass of the black hole alone, but by the mass of the whole vast envelope, which is far larger. The ceiling lifts. A black hole inside a dense hydrogen shroud can feed faster than a naked black hole ever could, fast enough perhaps to outrun the timing problem honestly, by genuinely growing at a rate the old rules forbade. The black hole star is not just an oddity in a catalogue. It may be the mechanism, the actual physical process and by which the universe grew its giants in the time available. And there is one more layer, the deepest one, still genuinely open. Where did the seeds themselves come from? Even with a raised Eddington limit, you need something to start with. And the only seed formation pathway we have ever directly observed, the collapse of a massive star, is too slow and too small to account for the earliest giants. So theorists have proposed another route. That in the early universe, a massive cloud of primordial gas could, under the right conditions, collapse directly into a black hole, skipping the star stage altogether. They call these direct collapse black holes. They are a well-developed theoretical idea. But we have never actually seen one. We have never had observational evidence that direct collapse really happens. And here is the thought that should stay with you. The little red dots might be that evidence. They might be the first time human beings have ever looked at the early universe and seen the process of giant black hole birth actually underway. Only continued observation will tell. But the possibility is real, and it is extraordinary. So let us draw the threads of the night together. We began with a population hiding in plain sight. Little red dots scattered across the dawn of the cosmos, invisible to every telescope until the right one was built, and then suddenly everywhere. And we end with that same phrase carrying a far larger weight. Because if objects this important could sit unseen in the early universe until Webb arrived, the honest question is no longer just what are the little red dots? It is, what else is hiding in plain sight right now in the deep field, waiting for the next instrument, the one we have not built yet? The little red dots are a humbling reminder that the universe is not as fully catalogued as we like to feel it is. There are still whole classes of objects out there with no name, and the only thing standing between us and them is the limit of our current eyes. And that should not feel like a discouraging thought, even drifting towards sleep. It should feel like the opposite. It means the universe is not a closed book that earlier generations finished reading and left for us only to memorize. It means there are still genuine first-time discoveries waiting, not in some distant future, but now in deep field images that have already been taken, in light that is already arriving, holding objects we have not yet learned to recognize. The little red dots were in Webb's data before anyone understood them. The understanding came later, and is still coming. Somewhere in the data we're gathering tonight, there are almost certainly other objects in exactly that state. Already photographed, not yet understood, waiting for the right idea or the next instrument to bring them into focus. The dawn of the universe still has unread pages. We simply have to keep building the eyes and keep daring to look. We asked early on whether anything could be a black hole and a star at the same time, and it sounded then like an impossible riddle. Now you have your answer. It can. It is called a black hole star, an object the universe was building in its very first chapter, predicted on paper by Mitchell Begelman 16 years before anyone saw one, and possibly the engine that seeded every supermassive black hole that anchors every galaxy that exists, including, in the most personal sense imaginable, our own. The black hole at the heart of the Milky Way had a beginning. It was young once, and the little red dots may be the closest we will ever come to watching the birth of an object like the one our entire galaxy is built around. This was never a documentary about somewhere else. It is the origin story of the place you're sitting in, and here is the last thing, the thing to drift off on. This story is not finished. The black hole star is the best explanation we have, and it fits the evidence better than anything before it, but it has not been confirmed. There are real questions still open. How common the black hole star phase is, how long it lasts, what triggers it, how the envelope forms when it disperses. The life cycle of a black hole star, if that is what these objects truly are, is still unmapped territory, and the science is moving at a pace that is hard to comprehend. Hundreds of papers on the little red dots have appeared in just the last 2 years, more than any single person could ever read. We're not looking back at a chapter of the universe that was written and closed long ago. We are watching the first chapter of cosmic structure be written and rewritten faster than anyone can read it, and we happen to be alive at the exact moment the pen is moving. The little red dots were always there, in the dark, at the dawn of everything. We simply had to build the eyes to see them, and what they may turn out to be telling us is the oldest story there is, how the universe learned to build the giants, and in the end how it came to look the way it does tonight, above your roof while you sleep.